talk today. It is going to be delivered by a distinguished scientist from Raman Institute. He will speak on the physics of soft matter. Before I request him to speak, I might just mention that this series of talks is of an informal nature for the benefit of students and teachers to learn a few things or to become aware of developments in a variety of fields apart from their own specialized area. That is our goal. Uh, and we are doing that in the most comfortable manner. We are not asking members to come to your place and be present physically. So this is the easiest way of learning few things of new concepts or new developments in various fields. And we have conducted talks on variety of topics, right from the quark model to the models of cosmology, as you know. So the range is very wide, and we have given the speakers full freedom to choose their topics, but they are requested to speak at the degree or PG level so that people can follow. And also we are also encouraging the usage of Kannada, the local language, as recommended by NEP. NEP is very strong about it, that we have to bring in, but it takes time. There are so many practical difficulties we have to face. So till the time we also make an attempt in that direction. So with these few words, I now request Professor Srikanta to introduce the speaker. Professor Srikanta.
Very good morning to all of you. I am very happy and I deem it as my privilege to introduce Professor V.A. Raghunathan, a good friend of mine, my contemporary in RRI, to the audience. In fact, when I was doing my research from 80 to 84 as a research scholar, he joined Raman Institute in 82. And so we were contemporaries working for our PhDs under the same guide, Dr. N.V. Madhusudana. Professor V.A. Raghunathan was born in 1960, and it is BSc and MSc from Bengaluru University. He passed his MSc from Bengaluru University in 1982, and in the same year, he joined Raman Research Institute as a research scholar under Professor N.V. Madhusudana for his PhD. And he completed his PhD, and PhD was awarded in 1989. After a stint as a postdoctoral fellow in France, he joined Raman Research Institute as a faculty member in 1995. And from 1995 onwards, he has been doing research in soft condensed matter physics, particularly liquid crystals and amphifields. And he became a full-fledged professor in RRI in 2008. He's a very unassuming person. In fact, when I asked him to share his profile, he sent only three sentences. Saying that he joined RRI in 82 as a student and in 1995 as a faculty member, and that's all he said. But somehow I picked up some information about his research interests and all that from the internet. And currently he is working as in INSA senior scientist in RRI. And of course he has authored a number of papers, maybe more than 100. I don't have the exact figure, but I'm quite sure that he has published more than 100 papers and presented papers in national and international journals, and he has guided PhD students also. His current research interests are organization of sterols in the membranes, structure and phase behavior of lipid membranes, diffusion in membranes, polyelectrolyte absorption on charged substrates, structure of lipid DNA complexes, self-assembled structures of amphifields. He is a fellow of the Indian National Science Academy, fellow of Indian Academy of Sciences, and also a fellow of the Indian National Science Academy. He is a very erudite scholar, a very serious researcher. That is what I have found from the day one. And I am very happy to present our speaker, B.A. Raghunathan, to the audience present on the online platform. So with this small, very short introduction, of course, it deserves a longer introduction, but because of the constraint of time constraint, I am limiting it to a very short introduction. Of course, I can go on for about more than half an hour to introduce V.A. Raghunathan, and he has got so many achievements to his credit. But I think with this short introduction, I request now V.A. Raghunathan to continue to take over the and give his presentation. Thank you very much.
Professor Raghunathan, you may speak for about 50 minutes and answer questions for about 10 minutes. You can plan that way.
Okay, I will do that.
Just carry on.
Yeah. So, first of all, thank you very much, Professor Srikanta, for your kind words. It's a great pleasure to be, giving a lecture to this audience, and I look forward to many more interactions in the future.
In fact, sorry for the interruption. Dr. Kagli forgot to mention one thing. We have been organizing these lectures almost every Sunday from October 23 continuously.
He told
October 23. Okay. So once again, I welcome you. Sorry for the interruption.
No problem. Thank you. Okay. So what I will do in this talk is to give you an overview of physics of soft matter, what soft materials are, and pick up a few examples from different kinds of soft materials to illustrate some basic concepts of physics. So I hope you will find it useful to pick up some of these systems, and I will try to show you that these systems are very good teaching aids for thermodynamics and basic physics. Okay, so that is my aim of this talk, and I hope you will be able to find some interesting concepts from this talk. So let me start with something that all of us know. So this diagram, which all of us are familiar with, when you study states of matter, we start, of course, with the ideal gas. That's the simplest system that we can have.
I'm sorry to interrupt you. We are not seeing your slides, sir.
You're not seeing my slides?
No. Maybe you stop sharing, or what is the problem? Please try sharing again.
Are you able to see now?
Now we can see. Yes.
Okay.
Thank you very much.
Yeah. So we start with. The ideal gas. Then, of course, the ideal gas, we have no interaction between the particles, and therefore we end up with. The gas doesn't show any phase transitions. It remains a gas at all temperatures and pressure. Then, of course, we learn about the virial expansion, where we take into account the corrections due to interparticle interactions. So we expand the pressure in a series as a function of the density. Okay, so that gives you I cannot, 1 minute, I'm not able to. Something has cropped up on my screen. Is it bothering you?
Yeah, we can see now. Yeah, no.
There's nothing on your screen, okay?
Yeah,
because there's something appearing on my screen.
It appeared. Yes, correct. Now it's clear.
Is it clear? Okay, good.
That's clear now.
Okay. So that way, so we go into still look at the interaction between the particles. So to take into account the interaction, we go to the virial expansion. Then, of course, we learn about the van der Waals equation of state, where we take into account the particle interaction and the size of the particle, so to say. And as we know, this equation of state can predict the transition between the gaseous state and the liquid state. So typically, that's all we learn about the gases. The ideal gas and the van der Waals gas. And then we learn about crystalline solids. Now, the crystalline solids are interesting because though the system has very high density, the fact that it has long range translational order, it has a lattice structure, makes it easier to describe this system. For example, you can solve the Schrodinger equation in a periodic potential and you get the energy bands and things like that. However, we, we don't, hello? When you go into liquids and glasses, which are also high density states, but these are disordered. And therefore, it becomes more difficult to describe these systems in great detail, to understand their behavior in great detail. And that is why we don't spend much time uh, learning about liquids and gases in our BSc or even our MSc. Okay. Whereas we learn a lot about crystalline solids. That is because the presence of long-range order makes it easier to understand these systems. Now, one point I want to make sure, just to draw your attention in this phase diagram, is the presence of the critical point, because this becomes, I will refer to that later on again in the discussions. So when you have it, if you take a gas and the liquid, symmetry-wise, they are the same. The only difference between them is the density. A gas has lower density compared to liquid generally. Therefore, there is a critical point in the phase diagram beyond which these two phases become the same. You can't distinguish between a gas and the liquid, and therefore you can go continuously from the gaseous phase to the liquid state. Okay, there is no phase transition in that sense. Whereas this does not happen between the solid and the liquid because that boundary continues forever. Okay, uh, so that is because there is a symmetry difference between the liquid and the solid. A solid has a crystalline structure, and therefore it's a different symmetry from the liquid state. And therefore that boundary cannot end at a critical point. Whereas when you come back to the liquid and gas, there is a critical point. And when you approach the critical point, the two phases become more or less similar to each other. And as a result, you have large-scale density fluctuations in the system. And the fluctuations in the density leads to fluctuations in the refractive index. And therefore, you have a lot of scattering from the system. So this is what is known as critical opalescence. So when you take a system very close to the critical point, it starts to scatter light enormously. Okay, if you haven't done this experiment yourself, you can. There are nice videos available on YouTube where they demonstrate the critical opalescence. It's a very remarkable effect, and you see a lot of scattering because of density fluctuations in the system. Because now the gas and the liquid are very similar, it's very easy to go from one to the other, and therefore there are large-scale density fluctuations. Okay. So typically these are the things one learns during our BSc or MSc. And now I come to what are soft condensed matter systems. Okay. Just 1 minute. Yeah. Is that fine? Okay. So there are, as you know, there are other systems which we are familiar with everyday life. Polymers, for example, a rubber band or DNA or protein, these are all made of, these are all polymers. Liquid crystals, all of you are familiar with liquid crystal displays. They are made up of liquid crystals. Colloids, milk, foam, clouds, paints, these are all examples of colloids. Then there are amplifiers like soaps, detergents, lipids. You put them in water, they form a lot of self-consumable structures. And then there are biological matter like cells, tissues, and all that. Now, where do you put in all this? Because the classical uh, states of matter that we study, there's no place for things like these. These are systems made up of dispersions of, for example, solids in a liquid and things like that. For liquid crystals, it's neither a liquid nor a crystal. Okay, so these are systems which do not fall into that our previous classification. But it was shown by P.H.L. Digens, who did a lot of work in this area, who won a Nobel Prize for his work in liquid crystals and other soft materials in 1991. So there were people who were working on these fields earlier, of course, but they were working in isolation. And he was the one who said that, see, all these fields have many things in common, and there are very basic physical concepts which are common to all these fields, and he called these as soft condensed matter. He said all these materials fall under the umbrella of soft condensed matter. So these are the various systems which we study under soft condensed matter. Now, what is common to all these things? There are certain features which are common to all these systems. One is a length scale. Unlike atomic or molecular systems, here we are talking about particle size which are the order of 10 nanometers to micrometers. Okay, so there's a long range which are much larger compared to simple atomic systems. And more important, the energy scale, the order of kBT. As you know, the ambient energy kBT is of the order of 1 over 40 electron volts. So the typical energy scales of these systems are that low, which means that these systems are easily deformable. And that's the reason why they're called soft matter, because they're soft, they can be easily deformed. For example, the modulus of a colloidal crystal is about 100 pascals, whereas in a solid it's about 100 gigapascals. So you see the large difference in the elastic response of the system. They are so much softer. It also means that because the energy scales are low, the entropy dominates in this system. Because as you know, the free energy F is U minus Ts. If U is negligible, the entropy part is what dominates the free energy. Okay, and I will show many examples where the systems are dominated by the entropy. Okay. The other thing is the time scale. The time scales are again much shorter compared to, much faster, much longer compared to the time scale that you have to make system. So things move much more slowly. The relaxation times are longer and things like that. Okay, so the time scales are much longer compared to atomic systems. And many of these systems show self-assembly. So they may be made of a small constituent particle which self-assemble to form larger aggregates. Okay, so these are some of the general features which are characteristic of soft matter. Okay, so what I will do now is I pick up few examples from various soft matter systems to illustrate some basic physics concepts. Okay, so let me first take up colloids. Okay, now the simplest type of colloids are what are known as hard sphere colloids. So the interaction potential will be as shown here. There are no interactions unless they are touching each other. So there is only hard sphere interaction. Only when they touch each other, they know their presence. Otherwise, there's no interaction. Now, interestingly, such particles can be prepared in the lab. Okay, so you can prepare these particles in the lab for a given well-defined size. Because when you make these particles, there will be a typical size distribution of this, and you can make this distribution as small as possible. Okay, so when the size distribution is small, these are called as monodisperse particles. They have almost a well-defined size. Okay, so such particles can be prepared in the lab, and that can be studied. Okay, so one of the interesting property of these colloidal dispersions, as we all know, is osmotic pressure. And you look at the osmotic pressure is given by the number density of the particles times kBT. Okay. And now this is what is known as a colligative property because it does not depend on the size of the particle or its chemical nature. Okay. So in this experiment, all that you do is you have this semi-permeable membrane. On one side, you put, for example, a sugar solution or a colloidal solution. Other side, you put water. And this semi-permeable membrane is such that these sugar molecules cannot permeate across. So they are constrained to be on one side. As a result, water starts moving from the other side to the sugar solution and the pressure builds up. At some point, there is an equilibrium because now here in this situation, there is gravity acting downwards. Okay, so because of that, you reach an equilibrium and there is an osmotic pressure which is occurring in the system. Now, the interesting thing here is the osmotic pressure does not depend upon what the particle is made up of. It can be a sugar molecule or it can be a colloidal particle. So in one case, the size is about 1 nanometer, other case is about 1000 nanometers. Okay, so 1 micron. So one colloidal particle is equivalent to one sugar solution. All that you require is that these particles are not allowed to move across the semi-permeable membrane. So this is at first very surprising because it just depends on the number, does not depend on the size or the chemical nature. Okay. Now this is not surprising because as I said earlier, in this case, in this hard-sphere colloidal system, one can neglect the internal energy because there are no interactions. So the Helmholtz free energy, for example, is essentially given by the entropy of the system. Now, what is the entropy? So this is one important formula that one should remember. It was given by Boltzmann, that entropy is given by the Boltzmann constant times logarithm of omega, where omega is the number of arrangements or number of configurations or number of microstates of the system. So this is the recipe that was given by Boltzmann. All the way to do is you have a system which is isolated. We need to find out how many microstate or how many configurations the system can take. And once we know that, we can calculate the entropy of the system. Now, this formula is so important that it's actually engraved on Boltzmann's dome in Vienna. Okay, if you go to Vienna and go to Boltzmann's dome, is engraved, and this is sort of engraved there because he and others thought that this is a very significant contribution that he made to statistical physics. Okay, so this is a recipe to calculate. So whatever happens, this recipe holds good. All that you need to know is the number of arrangements, number of configurations, and then from this formula, you can calculate the entropy. So let's see how we can do this in this particular case. Okay, so let's I have a solution whose volume is V. Okay, let's say the volume of the particle, each particle be U. Okay, so then I can divide this whole volume V into number of cells, each cell having a volume U. So this way I can create N, capital N number of cells. Okay, and I have a small n number of particles. And this capital N is much, much larger than small n because I have a dilute solution. So now I want to figure out how many ways can I arrange these small n particles in these cells. Okay, so let me calculate that. So the first particle can be placed in any of these capital N cells. Second particle can be placed in any of the remaining n minus 1 cells. The third one in the remaining n minus 2. So this way, I can calculate how many ways can I put these small n number of particles in this capital N number of cells. And since capital N is much, much larger than small n, omega is basically n to the power of n, or the entropy is logarithm of that. So entropy can be given by this expression. Okay, so the entropy is given by that, and therefore I can calculate the free energy. And from the free energy, I can calculate the pressure, and then I get this equation of state. Okay, so this entropy of the system, okay, is what is giving rise to this osmotic pressure. And as you can see, this is basically the ideal gas behavior. And the pressure of the ideal gas is also essentially due to its entropy, because even in that case, there are no interaction between the particles. Okay, so the only thing that the system has is entropy. The free energy contribution is just from the entropy, and that will lead to a pressure. Okay, so the system wants to increase the entropy. We know that in the isolated system, the entropy wants to be maximum. Since the entropy is proportional to the volume, it wants to increase the volume. And this is the reason why the water flows in from the outside to the inside, and this builds up the osmotic pressure of the system. Okay, so as I told you earlier, these systems are dominated by entropy, and this is an example where the entropy is giving rise to a pressure in the system. Okay. Now another example which is even more surprising is I take these hard sphere colloids at various concentrations. So phi is a volume fraction. So the fraction of the total volume occupied by the particles. The rest is water. Okay, so I make this. So I make these solutions of these colloidal particles in water, and then leave it for a few days. Then what I find is that I start getting these iridescence. Okay, you see these colors. So this iridescence is basically coming from Bragg scattering from crystallized that form. So this system forms crystals at higher concentrations. Now, if I do look at it more carefully, I can draw some kind of a phase diagram. Then I find that the crystals are forming above a volume fraction of 0.5. Now, this is interesting because at this volume fraction, the particles are not in contact. Okay, and there are no interaction between the particles. Still, the particles form arranged on a crystalline lattice. So this at first is very surprising. Why should these particles form a crystalline phase? Because there are no interaction between them, and they are not touching each other. They are not sort of close packed or anything like that. Still, they form a crystalline lattice. So this is a puzzle, but it's easy to understand why this happens if you look at this packing in some more detail. Okay. So let's look at close packing of equal spheres. Now this topic itself is very interesting because this whole thing was started by Kepler, the same Kepler whose planetary laws of planetary movement, So in 1611, Kepler conjectured that the best arrangement of equal sphere, the close packing equal sphere, is this hexagonal close packing or face-centered cubic packing. All of us know that. And these have a volume fraction of about 0.74. So when you pack these spheres, when you close pack, that means the spheres are touching each other. The best you can get is a volume fraction of 0.74. The rest will be the voids in between, which you can't avoid because these are spheres. There will be voids in between. Okay. It turns out that this conjecture was formally proved mathematically only in 2005, and the final proof was given in 2015. Okay, so it took so many years, almost 400 years, for this conjecture to be proved in a mathematical sense. Of course, in practice, we all knew that there's a best way one can pack spheres, but of course, mathematics need hard proof, and this proof took 400 years. Okay, so it's this whole field has a very interesting history of its own. So the important thing to remember is that this close packing of either an FCC or HCP corresponds to a volume fraction of 0.74. Okay. Now there is another kind of close pack, which is not that obvious. It's called random close packing. So here what we do is take these spheres in a sack, so to say, deformable container, and you tap it till they reach maximum compaction. Okay, so it turns out that you can do this, and there is an arrangement which is not crystalline, it's a random arrangement, but in this arrangement the particles are touching each other. So again, these are close packed. The close packed in the sense that the particles are touching each other, but there is no lattice, there's no periodic arrangement. Okay, so this is some kind of a random arrangement, but close packed. Now this corresponds to a volume fraction of about 0.63. Okay, so it's very surprising that such a close packing exists. Okay, people are still trying to understand this. I mean, you will find papers being published in all scientific journals even today, to people trying to understand details of the random close packing. Okay, so one way to understand this is this is the disordered state, disordered packing, with a maximum possible value of 5. So the volume fraction is maximum, but it is disordered. Okay, so we know that if the packing is regular, periodic, then we can achieve a volume fraction of 0.74 when they close pack. But if it is disordered, we have only a volume fraction of about 0.63. Okay. So now let's do a thought experiment. So let's imagine our colloidal system is in a random close pack state at a volume fraction of 0.64. Okay. So now at 0.64, these particles are touching each other, is jammed. They can't move. That means there is only one possible arrangement, because other arrangements are not accessible. Particles cannot move. So our omega is 1, and therefore entropy is 0. So the system has 0 entropy. Now let's say we can go to these particles, take each particle, and now arrange them on a FCC lattice. If you do that, we know that FCC lattice gets close packed onto at a volume fraction of 0.74. So at 0.64, it's not close packed. Okay, so I can go from this jammed, disordered state to a crystalline state, which is not close packed. Okay, so once I go to this FCC lattice, which is not close packed, these particles have the freedom to move above their equilibrium position. Okay, so that means the system is no more jammed, the particles can vibrate. So now the entropy is higher because of vibration, they can take many more configurations compared to the earlier system, the jam system. So here omega is much larger than 1, the entropy is 0. And so entropy is larger than 0. Okay, so by going from a disordered state to an ordered state, the entropy is increasing. So this is an important concept. Okay, so this crystallization is induced by entropy. Okay, so at 0.64 volume fraction, the crystalline state is preferred because it has a higher entropy compared to the disordered state. Okay, it turns out that this preference starts at around 0.5. So even at volume fraction of 0.5, the ordered state has more entropy than the disordered state. Okay, the argument I gave you was at volume fraction of 0.64, but if you go to the detailed calculation, this preference for the crystalline state starts at around 0.5 volume fraction. So very often we say that entropy is a measure of disorder. So one has to be careful because here I show you a system where because of entropy, it goes from a disordered state to an ordered state. The ordered state have more entropy compared to the disordered state. Okay, but this definition of entropy that Boltzmann gave us is always true. The crystalline state has more entropy because there are more configurations possible in this system. The particles are able to move around their equilibrium position, whereas in the disordered state, that the freedom is limited. Okay, and therefore they don't have that much freedom to move around. Okay. So this is what I want you to keep in mind, that be careful when you talk about entropy as a measure of disorder. Okay, because sometimes entropy can lead to order. Okay, but then this definition that Boltzmann gave us is always true. Okay, so that is one thing that I want you to keep in mind. I had one more example which I'll skip because the lack of time. Then I will go to another system known as liquid crystals. Now, all of us are familiar with liquid crystals. Liquid crystals, especially liquid crystal displays. Okay, so typically liquid crystals are made up of rod-like molecules. Okay, so these are liquids with long-range orientation order. Imagine a liquid which is made up of long molecules, and all these molecules want to point in the same direction in space. So that is what we mean by long-range orientational order. Okay, all these molecules, as is shown in this figure, all these molecules want to sort of orient in the same direction. Okay, so because of this, one can define a direction, a unit vector, which shows the preferred direction of the molecule. Okay, so these systems don't have positional order; they only have orientation order. That's why they are liquids. Okay. And because they have this orientation order, they are optically uniaxial. They show birefringence. You see, look at these a thin film of a liquid crystal between cross polarizers. You see these beautiful textures because of due to their defects in this medium and things like that. Okay. Now the interesting thing is that the molecule which I give an example of a molecule which shows a nematic liquid crystal, a nematic liquid crystal phase. These molecules do not have up-down symmetry because one end of the molecule is not the same as the other end. But the phase has up-down symmetry because there are as many molecules pointing up as there are pointing down. So on an average, there is up-down symmetry. So this is what the distribution function shows. There are molecules pointing along at angle theta 0 as well as pi. Okay, so there are up as well as down. The two directions are equivalent. Okay. So because of this, one can define an order parameter. An order parameter is a way of defining the ordering of these molecules. So the order parameter that we can define here is 3 cos squared theta minus 1. That is because when you had complete ordering, cos square theta is 1, and therefore this order parameter will be 1. And when it is completely disordered, cos square theta is 1/3, and therefore this order parameter will be 0. Okay. So then, in terms of this order parameter, we can define a mean field theory. So this is very equal theory of ferromagnet. So let me just show you the Weiss theory of ferromagnet that all of you are familiar with. So this Weiss theory is what is known as the mean field theory. So what we say is that at a given, so in the case of a magnetic system, we have spins. Now the spins are different from a pneumatic because these are vectors. There is an arrow and the arrow is a direction. There is no up-down symmetry. And in this case, the order parameter will be just the average value of cos theta itself. Okay. Now in this case, as you know, the Weiss theory predicts that the order parameter, the magnetization, decreases gradually as you increase the temperature and goes continuously to 0. So this is the ferromagnetic to paramagnetic transition is a continuous transition where the order parameter goes continuously at very low temperature will be 1 and it decreases and goes to 0 at the critical, at the transition point. In the case of a pneumatic crystal, similar things happen at low temperature. The order parameter keeps decreasing, but then as it approaches the transition temperature, it suddenly jumps. So this transition is not continuous. It's a first order transition. Okay, that is because the order parameter is different. It's not cos theta, it's a cos square theta because the up-down symmetry. So this is an example where the symmetry of the order parameter, in one case, pneumatic case, is a spin, that is a vector. In the case of pneumatic, it has up-down symmetry. It's more like a second-rank tensor. So because of the symmetry, difference in the symmetry of the order parameter, but the one case, the phase transition is continuous from the ordered to disordered phase. In the other case, it is discontinuous, the first order transition. Okay. So the pneumatic liquid is a very nice system to study phase transitions and the basic concepts of phase transitions and things like that. So it's a very simple system because it only has orientation order. It doesn't have a lattice. So it's the simplest system the simplest anisotropic system that one can imagine. Okay. Now the pneumatic liquid crystals have a different kind of elasticity. Okay. So let's say that there is a preferred orientation of these molecules, and you want to change this orientation by an angle theta. So any gradients in this angle theta leads to an elastic energy. Okay. So in the full-fledged theory, there are 3 basic deformations of pneumatic. It's called splay, bend, and twist. But if you take all these elastic constants to be the same, then in this one elastic constant approximation, this elasticity can be written in just terms of the gradients in the theta. The theta is the angle between the pneumatic director and the preferred direction. Okay, so that if you deform it, if you take it away from the preferred direction, then there is an energy cost. Okay. Now there is a very interesting aspect of the liquid crystal, that is light scattering. If I take a liquid crystal in a test tube, it looks whitish, it almost looks like milk. Okay, so this was a big puzzle in the early days because as we know, milk is a colloidal suspension and it scatters light because there are these small micron-sized particles dispersed in water and there is a refractive index mismatch between the solvent and these particles. Because there are 2 things. There's a refractive index mismatch between these small colloidal particles and the suspending medium, and these particles are on the size of wavelength of light. So these 2, if these 2 criteria are given, then you have a lot of scattering from this medium. So people thought that something similar was happening in the system, but it was a puzzle because people on one hand thought that this was a single phase, not a dispersion of colloidal particles. So the question was, how can a single phase lead to so much of scattering? Okay. So I referred to critical opalescence earlier. The critical opalescence happens because there are strong density fluctuations, and these density fluctuations lead to refractive index fluctuations. Now, this density fluctuations can happen, such large density fluctuations can happen only near the critical point where the compressibility is very small, as all of us know. Okay, so such large density fluctuations cannot happen in a if you're far from the critical point. So the puzzle was, why does a pneumatic scatter too much of light? It turns out that these are due to the fluctuations, the orientations of the molecules. So this was one of the first contributions by Digens, who, as I said earlier, won a Nobel Prize for his work in on liquid crystals and other salt materials. This was his first contribution to the field to show why pneumatics scatter so much of light. One can understand this by the application of equipartition theorem. So we apply equipartition theorem and we know that every degree of freedom has an energy of half kBt. So in the case of a fluctuating string, for example, one has to calculate the various modes of fluctuation, and one says that each mode has an half kBt of energy. Okay. In the case of normally when we talk about particles vibrating, the particles vibrating about the equilibrium position. For example, the way we calculate the specific heat of a solid, we basically apply the equipartition theorem. Okay, but when you use, for example, the Debye theory, then we look at phonons and we give each phonon a phonon of a particular wavelength, half kBt of energy based on equipartition theorem. One can do a similar thing here and calculate what are the amplitude of these fluctuations. These are orientational fluctuations. Okay. And as I told you, when you have orientational fluctuations, these fluctuations lead to fluctuations in the refractive index, and therefore that leads to a lot of scattering. So what we find is that the intensity of scattered light goes as 1 over q square, where q is the wavelength, or q is the inverse of the wavelength. Okay, so we have the large wavelength fluctuation in the system, which so essentially we have patches in the system which are the refractive index different from the background, and the size of these patches is very large. Okay, so this is very similar to what happens at particular palisades, but the fluctuations are not due to density. These are not density fluctuations giving rise to refractive index fluctuation, but these are orientational fluctuations giving rise to large change in refractive index. Okay, so this is a consequence of the small elasticity or the softness of the system, that the thermal energy is enough to excite these orientational fluctuations, which can lead to so much of scattering in the system. Okay. Another part of liquid crystals I thought I should emphasize is the fact how a twisted thematic display works. See, all of us use LCDs. I thought we should know how an LCD works. Okay. So an LCD basically has the picture on the left. You have this pneumatic, a thin layer of pneumatic liquid crystal sandwiched between two glass plates. Okay. On one side, on one glass plate, the pneumatic molecules are, say, oriented along the x-axis. On the top glass plate, the pneumatic molecules are oriented along the y-axis. So because there is the orientational order in the system, because of this, the orientation gradually goes from the x-axis to the y-axis as you go from one surface to the other surface. So what you have done is you have created a 90-degree twist in the system. Okay, the direction of the molecule rotates by 90 degrees as they go from the lower glass surface to the top glass surface. Okay, and now I keep two Polaroids on either surface. The lower Polaroid lets in light the EC axis, is along the x-axis, and the top Polaroid allows light which is polarized along the y-axis. So when I take this kind of arrangement, when I send in light from below, the light gets polarized, it goes through this medium. So the one important property of this medium now is that because of the 90-degree twist in the medium, the plane of polarization also gets rotated by 90 degrees. So when the plane of polarization enters this thin layer, it was along x-axis, but when it comes out, because of the 90-degree twist in the medium, the plane of polarization now becomes along the y-axis. And now the second polarizer is kept along the y-axis, and therefore the light comes through. So this layer appears bright. Okay. Now what we do is we apply a voltage between these two plates. So these two plates have transparent ITO, indium tin oxide electrodes, and therefore you can apply a voltage. It turns out that when you apply a voltage of around 1 volt, there's a competition between elastic energy and electric energy, dielectric energy. And if the voltage is high enough, the dielectric energy takes over, and all the molecules suddenly flip above a threshold voltage from the initial orientation to an orientation along the field. The field is aligned along the z-axis between the two plates, and therefore the molecules now flip around and align along the field direction when the applied voltage is just above the threshold, which is about 1 volt. So when this happens, the twist in the medium is no more there. Okay, and therefore the plane of polarization does not get rotated by 90 degrees. Initially the plane of polarization was along the x-axis. It now comes out along the x-axis because there is no more this 90-degree twist in the medium. So by doing this, what you have done is by applying the field, you have rotated the plane of polarization of the light which is coming through this thin layer by 90 degrees. So now the outcoming light has a plane of polarization along the x-axis, and it is cut off by your second polarizer. So the thin film which appeared bright initially now appears dark. So this is how a liquid crystal display works. By applying a field, you remove this 90 degrees twist, and therefore you rotate the plane of polarization by 90 degrees, and the second polarizer now, which was allowing the initial beam, now cuts it off. So what was bright initially now becomes dark. The only thing is now to make your surface into small segments so that you can address each pixel separately so that you can display whatever information you want to display. Okay, so the basic mechanism of the LCD is just this. You apply a field and you destroy the negative degree twist that you had. And all the color that you get are used, now obtained by using filters, because a liquid crystal itself is just a wall. It lets it light or just touches down. It doesn't create any color. Okay, so I hope next time you use an LCD, you will appreciate how it works. Okay. Another example I thought I will tell you about is rubber band elasticity. Let's do a simple example. You take a rubber band, okay, you suddenly stretch it, okay, and you can do it by keeping it, touching your lips, because if there's a small temperature change, you can sense it. So when you stretch the rubber band, you realize that it gets warmer. Okay, so then going to the thermodynamics, you have, it's an exothermic process, heat is given out. That means your enthalpy change has to be negative. It is a non-Sponheim process because you are stretching it, and delta G is positive. So when you work through this, you will realize that the entropy should have reduced. So by stretching the rubber band, you have reduced the entropy. Okay, so this is the conclusion of this experiment. Let's do another experiment. Here what you do is take a rubber band, you put a weight on it. So you have a rubber band which is stretched. Now we heat the rubber band. You will find that it actually shrinks. Okay, unlike a metal or something which when you heat will elongate, the rubber band shrinks. Okay, so again you can work through the thermodynamics. You will find that the entropy in this case increases. So by shrinking, the entropy increases. By stretching, the entropy decreases. Now how is this possible? Okay, so let's try to understand how is it possible. Now a rubber band is made up of polymer chains. Okay, and each polymer chain, to a good approximation, you can think of as a random walk. So you start at some point, you take steps, you take one step in one direction, then you take a next step in a randomly different direction. Okay, this is called a random walk. For example, in a one-dimensional random walk, what you do is I flip a coin. If I get heads, I move to the right. If I get tail, I move to the left. I keep on doing this many times. Then I can figure out after capital N number of flips, what is the probability I move n small n steps to the right. Okay, and this turns out to be having, and as this capital N goes to infinity, this distribution becomes like a Gaussian. Okay, so which means that if I take large number of steps, most probably you will come back to the same starting point that you started from. You come back to the, you start from the origin, and after many steps, you come back to the same thing. But that is the most stable, probable situation. And for example, if you want to, if all the steps are in the same direction, then you know that there's only one way you can do that, because every time you go in the same direction. So if I want to stretch a rubber band fully, all my, each link, all the links are in the same direction, and therefore only one way I can reach a fully stretched rubber band. Okay, so this is another way of saying that what is the number of configurations the system can take. Okay, so it turns out that if the rubber band is not stretched at all, so the starting position and the end position are the same, then there are maximum number of paths or maximum number of configurations the chain can take. Okay, to do this. Whereas as I keep extending it, increasing the length, then the number of configurations reduces. Okay, so again you can do the entropy from the system. So you'll find that the entropy is maximum when the rubber band is fully shrunk, and as you stretch it, the entropy keeps reducing. Okay, and then you can also find out that the free energy of the system, because again, as I said, the internal energy we don't have to worry about, or how is the entropy contribution, and I get the free energy has a dependence like R square. This almost behaves like a Hookean spring. Okay, so here as you stretch it, there is an elasticity, but this elasticity is coming just from entropy. But at the end of the day, it behaves like a Hookean spring. Okay, so as I stretch it, the entropy keeps reducing. Okay, so this is the reason why when I stretch it, the entropy reduces and the system gives out heat. That is why you feel the rubber band to be hot. When you heat it, then the system wants to go to the high entropy state and therefore it shrinks. Okay, so these systems, so these are very interesting systems to learn very basic concepts of thermodynamics. Okay, I do not know how much time I have. Can somebody tell me how much time I have?
Take about 10 minutes you can take. 10 minutes more.
10 minutes. Okay. So just a couple of things I will just cover. One is self-assembly of amplifiers. So all of you know amplifiers are molecules which have a hydrophilic and hydrophobic part. And it turns out that this hydrophobic effect is also entropic in origin. Okay. So it turns out that when I put a hydrophobic molecule in water, the water molecules around this hydrophobic chain becomes more ordered than water molecules in the bulk. So this is a model of hydrophobicity. So let's say I have the sphere is a hydrophobic molecule. I put it in water. Then the water molecules form a cage around this. Okay, so the water molecules in this cage are more ordered than water molecules in the bulk. And therefore, by putting these hydrophobic molecules in the system, you have decreased the entropy of the system. That is why, because the system doesn't like to decrease its entropy, that is why hydrophobic molecules do not dissolve in water. Because if you try to put it there, the entropy of the system increases. Okay, so the hydrophobic effect is also basically of entropic origin. Okay, and this is something is not fully understood even now. One would think that everybody knows that oil and water do not mix, and this should be something very well understood. But even now, you will find a lot of papers in many journals, people trying to understand many details of this phenomenon. Okay, so don't think that something is very common, is well understood, because many of these things are very common. We see it in everyday life, but there is still very deep physics there, which people are still trying to understand. Okay. Now I'll just talk, I'll skip all because there's not much time. I will just talk about one more subject which has become very, very very active in recent times. So let me just try to show you one video. I think I should have the. Are you able to see this?
See.
Hello?
Yes.
Yeah. So this is basically flocking of birds. Are you able to see my screen?
Yeah, yeah.
Yes.
Sorry, you're muted.
Yeah. We can see.
Are you able to see my screen?
Yes, we can see.
Hello?
Yes, we can see them. We can see the birds flying here, gathering.
Sorry, you're muted. I can't hear you. I hope you're able to see this.
Yeah, we can.
So my idea was to just show, so these are just birds. And they make all these, they form these flocks. Okay. And the question is, can you understand phenomena of this type? Okay. Why do these,
Very interesting.
hello, are you able to see this?
Yes, we can. Yes, we can see.
Sorry, are you able to see this?
Yes.
Okay, good. Okay, so now I come back to my thing. So the idea is that can we understand phenomena of this type? Okay, so till now what I have talked about are systems which were in equilibrium. Okay, they were driven by 1 minute.
We had to close the video.
Yeah, sorry. So they were in equilibrium. That means they were dead. I mean, they were not alive. But these days, people are trying to understand whether we can describe these what are known as active systems, because these are each particle takes energy from outside, and it is self-propelled. For example, we saw birds. Each bird has food, and it is self-propelled. So there are many systems of this sort: flock of birds, school of fish, bacterial suspension, migrating cells. Okay, so these are all self-propelled particles which are in some sense alive and active. Okay, so this field has gained a lot of interest in recent times because in some sense we are trying to explain biological systems. Okay, which are active, which are alive, which are self-propelled. Unlike the previous systems I talked about, which are in equilibrium, which are essentially dead. Okay, so these are different from systems driven by an external field because each particle is self-propelled. Okay, so there's no external field which is driving each particle. Each particle is sort of self-propelled. So this field started from this piece of work where people wanted to understand the flocking of birds. Okay, so they proposed a simple system. Let's say there are particles, each is self-propelled, each moves with a constant velocity v, and each one is driven by its own. Each particle consumes energy and creates this propulsion. And the direction of its velocity is determined by its neighborhood. So you take one particle, take a small volume around it, take the average direction of all the particles there. So the volume of the direction of this particle is decided by all the particles in that neighborhood. Okay, so just based on this, and you have some noise in the system. So people found that this system also shows a phase transition. Okay, when the noise is less, you have an ordered phase where all the birds, so to say, are flying in the same direction. So there's a flock which is flying in the same direction. But as I increase the noise, they start flying in different directions. Okay, so there is a transition from an ordered phase to a disordered phase, but in a system which is self-driven. So this is very different from the kind of systems I talked about. Okay, this is a self-driven system. So this is known as active particles. Okay, so this field has become very important of late. So this was the first work. In the last couple of decades, it has grown in importance, and there are large number of contributions from a lot of our colleagues from Bangalore itself who have made very important contribution to this field. So it's a field to look forward to. This is sort of considered to be part of soft matter, but active matter because these are self-propelled particles. Okay, so I hope I gave you an overview of some of the things in the field. I hope you're able to appreciate some of them, and I'll leave you with a couple of references, which are sort of introductory books in soft matter. There's a book by Richard Jones on soft content matter, and another book by Ian Hamley, which are introductory books which covers most of the things I talked about. So thank you very much. If there are any questions, I'll be more than happy to.
Thank you very much for a very nice and interesting presentation. Now, if there are any questions, please raise your hand, then we can go one by one. Before anybody asks a question, I have this last question. You said you are going to introduce some noise in the flight of the birds. What exactly is the noise that you have in mind? Birds flying. You are going to introduce noise, and then there will be some kind of ordering. What exactly is meant by noise there? Oh, you didn't hear? Are you not hearing? Yeah. Did you not hear? Probably you didn't hear the question.
Yeah, please tell me. Sorry. Yeah, I didn't hear the question. Sorry.
Yeah, the question is in the example of the birds flying together.
Yeah.
You said that when you introduce some noise,
yeah,
then there is going to be some order.
No, it's the other way around. When there is less noise, there is order. So the noise behaves like the temperature in this case. So at low noise and low temperature, there is order. As I increase the noise, is an increase in the temperature. So it goes from a ordered state to a disordered state. There's almost like a phase transition.
Right. Professor Srikanta, you want to ask a question? You can ask. So Srikanta, you can unmute and ask a question.
Now can you hear me?
Yes, I can hear you. Yeah.
In one of the slides, sir, you showed that the spheres were jammed in the this thing, system
yes.
jammed and all that.
Yeah.
There, it's a randomness, right?
Yes.
It's randomness.
Yes.
But you said entropy is zero in that case.
That is because it's the particles
are.
Because
randomness increases entropy, no?
No. So that's the thing. See, the particles are touching each other. So they are in a jammed state. They can only take one configuration. See, if you can take different configurations, then yes, the entropy will be high. Okay, so this is what I was trying to say. When they are jammed, the particles cannot move. So there is only one state. So because there is omega is 1, the entropy is 0. But if they can go from one state to another state, then the entropy will be high. So this is why I was saying that one has to be careful when you say disordered states have high entropy, because the system should be able to access different states.
If so, even because of the jam, they're not able to go to another state.
Precisely. Yes. Because they're jammed, they can't go to another state.
Okay. That's why entropy is 0.
That's why entropy is 0. So if I go to the jam state and unjam it, I can unjam it by going to a crystalline state. So that is why the crystalline state has more entropy in this situation.
So one more thing regarding the stretching of this rubber band.
Yeah.
What I understand, for example, if I take analogy of the expansion of a gas,
Yeah.
analogy with the expansion of a gas,
Yeah.
when the gas expands, the molecules are drawn apart,
Yeah.
and then there will be a cooling effect, right? Cooling effect.
Yeah. Yeah.
But in the rubber band, when you stretch it, it heats up.
Yeah.
And I thought when you stretch it, the molecules move away from each other. Therefore, their potential energy is, when you stretch, it is increased. Attraction is there. Now you are spending energy to overcome that attraction. The energy comes down. I thought like that way.
No, so in this case, what happens is that the entropy contribution is dominating in this case.
Uh-huh.
Because a polymer chain, as I said, the highest entropy is when the polymer chain is completely shrunk. It completely shrunk in the sense that the polymer chain, as I said, the two ends are
The
nearby.
entropy is less when there is no stretch.
The entropy is less when there's less stretch. So entropy is more when it's less stretch. As you stretch it more and more, the entropy reduces. For example, if I take a chain and stretch it to the maximum extent, fully stretched.
Yes.
When it's fully stretched, there's only one configuration.
Yes.
Okay, so that is the least entropy state.
Oh,
As I bring
the least entropy is that's a
stretched
non-equilibrium state.
fully stretched state.
Yeah, it's a non-equilibrium. I mean, because entropy maximum is equilibrium state.
So yeah, so if I apply a stress, external force, then I can stretch it.
Yeah.
But by itself, it will choose a state where the entropy is maximum, and therefore it will be the two ends will be as close to each other as possible. Because when the two ends are close to each other, there are many configurations the system can take. The number of configurations is maximum in that situation.
As a follow-up question regarding the rubber band,
yeah.
When you stretch the rubber band, they get aligned. How that happens? What is it? What is the physical phenomena that is going to make the molecules align when you stretch? We think.
That is because, see, in the rubber band, there are points between them. The simplest example, you take rubber band to be just one polymer chain. Okay, because we can do experiments with one single chain these days. So left to itself, for example, if you have a polymer chain in a solvent, left to itself, the polymer chain will form a configuration really highly swollen, but the two ends will be close to each other. Now, if I take the two ends and stretch it, so in order to stretch it, I need to stretch the chains.
Yes.
I need to take the two ends and pull them apart.
Yes. Yes.
Okay. And that is when the entropy decreases.
Any other questions? Okay. Can you give some more examples of one more example of an ordered state that has a higher entropy?
Yes, actually, this is one example I didn't mention. I can just show you. It's actually again with colloids. See, the thing is, the entropy is always maximum. Okay, so that is always true. So, for example, I'll just show you this. So here, what I have are collection of big particles and small particles. So it's a colloidal solution. There are small colloidal particles and big colloidal particles. Okay. Now the number of big colloidal particles is small compared to the number of small colloidal particles. Okay. So small ones are large compared to the big colloidal particles. Now what happens is that around each colloidal particle, we are familiar with the idea of excluded volume. So when you have two particles, the second particle cannot, there is a volume around the first particle from which the second particle is excluded. Okay. So around each big particle, there is an excluded volume around which the small particles cannot come. But when the big particles come together, the excluded volume around the big particles overlap. Okay, so when you have these big particles, if they all come together, then the small particles have more volume to go around. So the entropy of the small particles will increase. Okay, so in this situation, what will happen is the big particles will form a crystal large. Okay, because by doing that, the small particles will have more volume and more entropy. Okay, so what you do is that you increase the entropy of the small particles, but decrease the entropy of big particles. But since there are very many large number of small particles compared to the big particles, the entropy of the small particles dominate. Okay, so you create ordering of the big particles uh, by disordering the small particles more. Okay, so this is another example where the overall entropy increases, but this can lead to increase in order in one part of the system. Okay.
Oh, thank you.
Sir, this can happen even in raindrops also, because even in raindrops, some big drops are formed due to some small drops. Will it happen even in raindrops also, like what you are showing here?
See, there the system is slightly different because each particle is falling under gravity. Okay.
Yes, sir.
And the particles, when they collide, they can break up and all this. So it's a much more complicated situation. So here, you just have the suspension. So they are just Brownian particles. They're just moving around because of Brownian motion, that's all. Okay. There's no other external force acting on them. Okay.
Yes, sir. Sir, I have one more question.
Yeah.
You said that pneumatic, is it a ferromagnetic substance? And
Oh,
also
no.
you
So
mentioned
that's
about
an interesting.
ferromagnetic to paramagnetic at some
So that's an interesting question because in a in a magnetic system, as I showed here, you have spins. Okay, so each atom is like a small magnet, and it's a vector. There is a direction. So all the spins in the ferromagnetic space, all the spins point the same direction. And when you go to paramagnetic phase, they point it randomly. So the net magnetization is zero. On the difference to the pneumatic is, in the pneumatic, the up and down directions are the same. So you can think of arrows having up and down. Okay, there are arrowheads on both sides. So the up direction is same as the down direction. Okay. Whereas in the ferromagnet, up and down are not the same. Okay. So that is a big difference between a pneumatic and a magnetic system. And because of this, the transition from a ordered to disordered in the pneumatic case is first order, whereas in the case of a magnetic system is second order, continuous. Okay.
Yes, sir.
Is that clear? Yeah.
Yes, sir. Yes, sir. I have one more, sir.
Yeah.
You also mentioned about, with respect to the pneumatic crystal itself, inhomogeneities in refractive indices.
Yeah.
What may be the numerical value of the inhomogeneity in refractive index?
See, the pneumatics, their birefringence is very large typically. It's around 0.2 or it can be order of 0.1, 0.2. Okay. So when you have this small change in the orientation of the molecules, your effective refractive index changes. Okay. So that change becomes significant. So as I said, the birefringence is very large, of the order of 0.15 to 0.2 even. Okay. And because of that, even small change in the orientation of the director can change the refractive index to a large extent. Okay. How much it changes depends on the actual change in theta. But as I said, from the birefringence, one can actually calculate. So because the birefringence is so much large, that is the reason why these fluctuations are able to create such large changes in the refractive index.
Thank you, sir. Thank you.
Okay, if there are no further questions, I request Professor Nagaraju to propose a vote of thanks formally.
Sir, thank you very much, sir, because you have started from ideal gas equation, then real gases, then even equations related to van der Waals equation, all those things you have mentioned. And in fact, you have brought from the basic fundamentals to the soft condensed matter physics, and also mentioned about colloidal, liquid crystal, everything you have brought in. And of course, all of us, even though we have not done anything on those lines, but we have understood what you have explained to us. So thank you very much, sir. And you know that we are actually Srikanta and Professor B.A. Conley already they have mentioned about the talks on different topics in our KPA platform. And of course, this Zoom line platform is supported by Dr. M.K. Raghavendra, Ajnanadhara, and on behalf of KPA, I thank Dr. M.K. Raghavendra and also Dr. Srikanta and Professor G.A. Kagli for arranging this lecture. Thank you, our KPA members and also the invited faculty members to this platform. And I hope that all of you have enjoyed this talk. Thank you, one and all. Thank you very much, sir.
And thanks a lot. We'll come back next week. Thank you very much.
Thank you.
Thank you, Raghu. Thank you, Raghu. Thank you.
Oh, thank you, Lord. Yeah, welcome.
Yeah, yeah.
Okay.
Good
Bye-bye.
evening.